Welcome to Online Algebra 2 class. Today, we're going to cover section 8-2, the reciprocal function family. So our objective here is to first talk about what reciprocal functions are, then to graph them, and then to finally graph translations of these reciprocal functions. If you don't remember what translations are, that's when we move the function up, down, left, right, stretch it, compress it, and reflect it. So these transformations, exactly, all these different things, stretches, compressions, shrinks, reflections, and horizontal and vertical translations. So in the previous section, we talked a little bit about the inverse variation. So inverse variation is when I have some sort of formula like this, where y is equal to k over x, where k is some constant. Okay. So a function that models this is my reciprocal function, where the parent reciprocal function is f of x is equal to 1 over x. That would make my constant 1. And of course, that x does not equal 0 because that would put a 0 in the denominator. Okay? So we're basically going to take this idea, and now we're going to look at both sides of the function across the whole domain. Looks kind of like this. Okay, so this is the general form of a member of the reciprocal function family. And here we have our general form equation, where y is equal to a over x minus h plus k, where h and k are the shifts left and right for h and up and down for k. Inverse variation functions y equals a over x are, so remember this is 1 over x. So if we have a over x, these are going to be stretches or compressions, stretches or shrinks, or reflections, if you put a negative in the front, of the parent function. And again, this is the parent function. Y is equal to 1 over x. So look at it carefully. Look what it looks like. So you can see that it's got these two pieces on each side, and it's got nothing happening here on the y-axis. That's because you can't plug 0 into this equation. Y equals 1 over 0 is undefined. So we can't do that. Then it's got nothing going on there on the x-axis. That's because no matter what number I plug in here, if x is 10, if x is 100, if x is 1,000, if x is 10,000, no matter what number I plug in for x, I'm never going to get 0 as I keep putting 0 bigger and bigger and bigger numbers. I'm just going to get a really, really small fraction. And if I keep putting negative numbers in for x, same thing is going to happen. I'm never going to get to 0. I'm just going to get really, really, really small negative numbers. Let's see what a graph of this might look like. Okay, so let's start with y is equal to 8 over x. And the way we're going to graph any of these things is we're going to start with our table. So we're going to make an x and y input table. Let's start with the positive numbers, and then we'll go to the negative numbers. If I plug in 1, that's 8 over 1. That is 8. And notice this graph goes by 2's, so that would be right about there. If I plug in a 2, that's 8 over 2. That'd be 4. I could plug in 3, but I just feel like plugging in 4 is better, right? That's going to be 2. I could plug in 5 and 6 and 7, but I'm just going to plug in 8 to get 1. All right, so that's 2, 4, 4, 2, 4, 2, because remember these line goes by 2's, and then 8 and 1. And you can see we're getting this top branch right there, okay? Let's try some negative numbers, okay? So if I plug in negative 1, 8 over negative 1 is negative 8. Okay, so if I plug in negative 2, 8 over negative 2 is negative 4. If I plug in negative 4, you get negative 2, and negative 8, you would get negative 1. So you get the same answers here, right? It's just that negative in the bottom makes the answer turn out negative. And so when we graph this, negative 1, negative 8, negative 2, oh, whoops, sorry, negative 1, right? But half, -8, -2, -4, -4, -2, and -8, -1. And if I even wanted to go crazy here and see what's happening as I get smaller and smaller, I could plug in 1/2, and that would give me 8 divided by 1/2 multiplied by the reciprocal, so we would get 16. So even here, 1/2, 2, 4, 6, right? We would get something like that. And same thing on the bottom, we would get a -1/2 there. And the same thing, the opposite is true as well. So if I plug in 16, I would get 1/2. And if I plug in -16, I would get -1/2. And now we have a pretty good idea of what this graph is going to look like. So I make my first curve like that, and I make my second curve nice and smooth going this way. Okay? Notice what happens. This graph does not cross the x-axis. It does not cross the y-axis, but it does have this big jump right here. All right, let's try another one. Oh, okay, sorry. Domain and range. So the domain of this function is everything except for 0, okay? So the domain, I can't, 0 is the only thing I'm not allowed to plug in this function. It says clearly right here, x is not equal to 0. So I could just write the domain is x is not equal to 0. If I want to use interval notation, which is better, it would go from -infinity to 0, and then from 0 to infinity, not including these points, and I'm going to put them together with a union. Okay? The range is everything except for 0. So the same thing from the range, -infinity to 0, not including 0, union 0 to infinity. Interval notation is better as a way to represent domain and range, right? So what this is saying is everything except for 0. It's not including 0 because I have a parenthesis and not a bracket. Okay. So for this one with a 12, it's going to look exactly the same. It's just that 12 stretches the function out more. So again, when I make my table here, and I'm just going to do the positive side here, and we can reflect it over, use numbers that work well. So we can plug in 1 and get 12. We can plug in, actually we can even plug in a number before that. We can plug in 1/2 and get 24. Right? I can plug in 2 and get 6, 3 and get 4, 4 and get 3. Now, why would you plug in 5, right? 5 gives you, 2 and almost 1/2, but not really. So 2 and 2/5. So, don't plug in numbers that are really, really hard to graph. And 6, especially on a graph that goes by 2s. 6 would give me 2, and then we can just reverse these again, and then just plug in 12, and it would give me 1. All right, so 1 would be 12, 2, 6, 3 is 4, 4 is, whoops, it's not even a 3. 3 is 4, 4 is 3, 6, 2, and 12 is 1. Okay, so I got my top part right here, and then I can just all make these all negative. All right, so -1, -12, -2, -6, -3, -4, -6, -2, and -12, -1. So I get my, and then it was 1/2 of 24, so, we're going to get pretty close to that. Down there. And again, it should be straighter like that. And we get our same sort of picture. Domain and range for this is the same. Everything except for 0 for domain, everything except for 0 for range. Would this function, and this function all have the same domain? Yeah, because the only thing you're not allowed to plug into this is 0. So they all have the same domain. And they all actually have the same range as well, because the only output you're never going to get is 0. Okay, so each of these pieces right here, each of those two pieces of the function is called a branch. Branches of the parent function 1 over x are in quadrant 1 and 3. Okay, we got quadrant 1, that's quadrant 2, this is quadrant 3, and this is quadrant 4. So you can see that my branches are in quadrant 1 and 3, right? Even with the parent function right here. Okay. Stretches and compressions remain in the same quadrants, just like the last problem. Reflections turn it into quadrant 2 and 4. So let's take a look at a couple of different values of A. So basically what I'm doing is I have the graph here of 1 over x. This is the graph of 1 over x. And you can tell that because, see, if I plug in 1, I get 1. If I plug in 2, I get a half. So I can tell sort of what that function is. It's kind of hard to tell just by looking at it, but this is the function 1 over x. So if I take a number like 6 and plug it in to the numerator, I now get y is equal to 6 over x. Okay? And from the last problem, you should realize what this is going to do to the function. Okay? So now instead of the first, if I plug in 1, instead of getting 1 over x, 1 over 1, I now get 6 over 1. So instead of this point being here, it's going to shift up way up to there. So what this has the effect of is this is a vertical stretch. So it's going to really take these edges and pull them out. It's going to pull this point up, which has the effect of making this curve look like it moved out. And it'll look, whoops, this should be on top, but it'll look something like this. You can see that this point has now been stretched up to there. This point has been stretched up to there, and the middles now look like they've been pulled out that way. For this one, now that's a fraction. So now y is going to be equal to 0.25 over x, or even better, 1 over 4x, right? 1/4, right? So it's going to be 1/4 times 1 over x. That's what 0.25 over x means. And so we can get the number in the bottom. And now that has the effect of compressing the function. So if we start with our parent function right here, and we look, the blue one is my new function. It has now been compressed. It has been pushed closer to the x-axis. And the last one, which is a negative. So if the function y is equal to 6, look like this one, the blue one, putting a negative in the front of it would have the effect of making it in the other quadrants, making it in the first quadrant and the second quadrant and the last quadrant, the fourth quadrant. Okay, and then just looking at these three, right? So I'm not going to draw the whole graph here, but we can say that a 1/2 would have the effect of compressing the function, 2 would stretch it, and negative 1/2 would compress it and reflect it. Okay, so we can translate any of the reciprocal functions horizontally or vertically, just like we do with any of the other functions. Okay, so here's my starting point. Okay, here we have a stretch or compression depending on what a is. We just saw that if a is a bigger number than 1, we're going to stretch it out. If it is a fraction or a decimal that is between 0 and 1, it's going to compress the function. Now what we haven't done yet, which we're about to, is h and k. H moves the function left or right. K moves the function up or down. A negative x shifts the function to the right. A negative h shifts the function right, positive left. For k, positive up, negative down. And here is what all of my transformations put together will look like. So when I look at a reciprocal function, if I want to graph a translated reciprocal function, a good idea is to first draw the asymptotes. So even in all of these, right, the asymptotes were 0, 0. How do I know that? Because if I look at this function, it hasn't been shifted left or right. Okay. So when I look at this function, it has been shifted left or right. That 1 shifts the graph left 1. This shifts it down 2. So a good technique, and one that we're going to use even in the next section when we graph more complicated functions, is to draw the asymptotes first, then plug in some points. So draw the asymptote first. It usually is at 0, but now it's been shifted left 1. And so I draw this with a dotted line. Normally it's at 0. Now it's been shifted down 2. Okay, so now I know my function here has a of 1. So that means that my answer is going to be in the first quadrant and the third quadrant. I just don't know exactly where. And the way I'm going to do this is plug in numbers. So just looking at my graph, the numbers that I want to plug in, I can't plug in this, it's an asymptote. Why not 0, 1, and 2? And that should give me enough information for the right side of my graph. And how about negative 2? I can't plug in negative 1 because it's an asymptote. Negative 1, negative 2, negative 2, negative 3, negative 4. So negative 2, negative 3, and negative 4. So when I plug all these numbers in, I should get a good idea. And I know my graph is going to look kind of like, this with these two curves, these two branches in the top and bottom. But I just don't know exactly where they are. So if I plug in 0, I get a 0 there. So that's 1 minus 2 is negative 1. If I plug in a 1, that is 1/2 minus 2, which is negative 3 over 2. And if I plug in a 2, that is 1/3 minus 2, which is negative 5 over 3. All right, so let's plug in some of the negative numbers. Negative 2 plus 1 is a negative 1 minus 2 is negative 3. So negative 3 plus 1, if I plug in a negative 3 here, that's a negative 1/2 minus 2. That's negative 2.5. And finally, if I plug in a negative 4 there, that's negative 1/3 minus 2 gives me, negative 7 over 3. Negative 2 1/3. All right, so let's graph these. 0, negative 1. Got a point right there. 1 and negative 1.5. So that's right there. And then 5/3 is almost 2, but it's not quite. And we get a point right there. So even though that it looks like that's not a lot of points to graph, it's kind of enough to get the general idea of what this function is going to look like. Let's do the negatives. Negative 2, we'd have negative 3 right there. Negative 3 is negative 2.5, so that's right there. And then negative 7 over 3 is a little bit bigger than negative 2. It's negative 2 1/3, so we get something like that. A little bit, yeah, okay, negative 2 1/3, right like that. So I know these graphs, and this doesn't look like much, but it's enough because I know this graph as I go left to right is going to get flattened out towards that asymptote. And as I get closer and closer to the middle, it's going to go almost straight up and down. So we're going to get a picture that kind of looks like that on the left and like this on the right. Okay, and that is enough to get a decent picture of my graph. Let's just set up this one right down here. And oh, I didn't identify the domain range. Domain range. Domain is all real numbers except for -1. Range is all real numbers except for -2. Right? The asymptotes tell you the excluded values for the domain and the range. Okay? So for this one, graph of -4. So that is right 4. +6. So here are my two asymptotes, which makes my domain everything except for -4, my range everything except for +6. I know my graph is going to be in the first and the third quadrants, and whoops, I can just make my table. Okay, when I plug in 5, right, I get a 7. And when I plug in other numbers over here, I'm going to get my curve to be kind of like this. Let's plug in the 6. Okay, so that would be 1/2 plus 6, which would be 6.5. So we would get something kind of like that. And again, you don't need a lot of points to graph these functions because you know that it goes up as it goes towards the top, and then it sort of flattens out. If you go right here, we might want one more. So let's plug in 7, and let's see what we get here. So that's 6 1/3. So 6 1/3. Again, we're getting flatter there, and it's going to kind of go this way. A graphing calculator would really help you get the best answer for this, right? So, but we're going to get this little sort of curve here, and then we're going to get the same thing going on the left-hand side. Best number to plug in is something that makes this not a fraction, actually, which would be 4. So if I plug in, I can't plug in 4, sorry, 3. Right? If I plug in 3, I get -1 on the bottom, and so I would get a 5. Right? 1, yeah, -1 plus 6, so we get 5. So we're going to get some sort of curve, and it's going to look something like this. All right, and so that's my basic graph there. If we know the asymptotes of the graph, and we know A, we can write the equation of the function. And this is pretty simple because I can see there's my graph. There's my asymptotes. As long as it tells me A, which it does, so I know it has to be 2 over something. Now I just got to decide that something. Notice that these lines go by 2's. So this is going left 3, up 4. So you just got to look at your functions here and say, which one of these functions goes left 3, up 4, and the answer would be A. Let's try that again. So here, again, we're starting with y is equal to 2 over something. Okay, I just need to decide what is h and what is k. So if I look carefully, since these are going by 2's, we're going right 1. So that means I want a -1, and I'm going down 4. So that means over here I want a -4. And there's my function. Okay. So finally, let's finish with the word problem. And when I look at this problem, we're going to use a reciprocal function to solve it, obviously. The rowing club is renting a 57-passenger bus for a day trip. Cost of the bus is $750. 5 passengers will be chaperones. If the student who attended share the bus cost equally, what function models the cost per student with respect to the other students and who attend? Domain and range. How many people must make the cost per student no more than 20 bucks? So basically, I want to divide my cost of the bus. Right? It's a 57 passenger bus. It's going to cost 750 bucks. So that means that anytime you take a bus, if you're going to split it up between the number of people, it's going to be the cost divided by the number of people who go. Okay? So the domain of this has to be, well, it could be from 0, but that doesn't make any sense. So we're going to go from, all right, why would you rent a bus for 0 people? We're going to go, and interval notation is not the best way to do this. So the domain is going to be from 1 person to how many people? Well, 57 people. The bus holds 57, but 5 of them are chaperones. So that means that only 52 people are going to pay. All right, so the best way to write this is with set builder notation, so that way we can specify it's everything between 1 and 52 that is an integer because you can't have half a person. And the way we would write that is domain is x such that x is between 1 and 52, and x is anybody remember the symbol for integers, which is z. Usually 2 sticks here, but whatever. Okay. So if you don't understand that, that's okay. We can just write it out, and that's fine. Now, how many students must ride the bus to make it no more than 20 bucks? Well, we could set this function up sort of like that. Kind of a little more difficult to solve this because you would want to set it equal to 0, and you know, I'll show you. So we would basically want to do something like that. Common denominator gives me, let me put this both ends. And now we can assume that since I want to make the numerator equal to 0, right? The denominator is just a variable. So if I set the numerator equal to 0, then this function will be 0, and I have a place to compare. So I would do 750 minus 20, and I want to know where this is equal to 0. And so I just subtract 750 from both sides, and we get that n is 37 and a half. Okay, so that's my sort of middle point. If I want the cost to be less than this, then I need more people. Okay? So that means I need at least 38 people. So that's the algebraic way to solve it. You could really graph it. Okay, let's clear this out. You could really just graph it here, and you can see that here's my reciprocal function, which is 750 over x or n, whatever. And here's the line 20. Okay, and you can see that as I have less people, it costs more. Right? As soon as I hit this point, now the cost is below 20. And of course, there's a cutoff point because you can only have a certain number of people on the bus. But you get the idea that the more people, the more there is to share the cost, the less it's going to cost per person. And that is 8-2, the reciprocal function family. Let's just go real quick here. This shifts the function up 5. This this stretches the function by a factor of 4 and reflects it, and the asymptotes here would be left 2, down 7. It has a stretch of 5, but that doesn't affect the asymptotes at all. All right, so that's A2, the reciprocal function family.